Okay, thank you, Benoit. Thank you for having me here. Thank you for the invitation. It's a pleasure to be here. So yeah, I mean, I thought I would talk about some key questions and challenges we have in understanding protoplanetary disk, in the dynamics and the emission of the gas and the dust contents of this disk. And so since I am primarily working on the formation and orbital evolution of planetary systems, some of these questions / challenges will be actually directed to these planetary systems that form in protoplanetary disk. So there's going to be actually three questions or three main points that I will try to describe in this presentation. One is the mass of protoplanetary disks, what drives the evolution of protoplanetary disk, and what is behind all the structures that we see in the emission of disks. So, okay, that works. Okay, so starting with a little bit of observational context, I think we can say that we are really like a golden era in observing protoplanetary disks because we have so many observing tools to detect and to spatially resolve the emission of protoplanetary disk. And this is the case in the dust and in the gas. This is actually summarized in this cartoon. So we can observe the dust emission, and this is something that we can do at several wavelengths. So we can have access to the thermal emission at 7 millimeter wavelength. So this is mostly probing the cold emission of dust in protoplanetary disk, and most presumably closer to the midplane. And so this is something that can be done with NOEMA, with ALMA as well. I'm showing you here an image of one's favorite disk in the moment, HD 163296, where you can see several structures, dark rings, bright rings in the dust continuum emission. But you can also probe actually the scattered light emission, which is thought to arise from the surface layers of the disk. And this is something that can be done in the optical and the near infrared, showing you actually the very same disk. I'm going to just show in this slide the very same disk at different wavelengths and different observing techniques. So this is the very same disk observed with HST in the optical. So this is showing the total intensity. And the little set here shows the polarized intensity. So you see like different structures and different global extent of the disk probed at these different wavelengths. But in the near infrared, we can also make use of the interferometric technique, and this is something that has been recently achieved with Matisse on the VLTR. You can probe actually the dust emission very close to the dust sublimation radius of the disk, and it's kind of remarkable that even there we can actually find non-axisymmetric emission in the form of non-axisymmetric rings. So I find it quite remarkable actually that over a wide range of radii in disk, we can actually find structures like axisymmetric and non-axisymmetric structures. You can probe gas, of course, and this is showing you here what we find for the 12 CO2 to 1 rotational transition as probed with ALMA, which is, constraining the optically thick nature of the emission in this disk. And we can also probe the disk with other gas species. And this is, for instance, here the case with CS. So the main point here is that we have these very diverse techniques that allow us to spatially resolve the disk. And this is, of course, key observing data for us to try and constrain the dynamics and to improve our vision of how the gas and dust evolve and work in these planet-forming regions. And of course, we've heard a lot about PWST this week, and so we're all looking forward for PWST data on disks. These different observing techniques, as I said, they can actually give us very stringent constraints on the key physical mechanisms that are working protoplanetary disk. And I think these techniques have allowed to illustrate some of the different key physical and chemical processes that work in the disk. And this is something that I briefly illustrate with this cartoon. This is the same cartoon as before. Now, the more theoretical part of the cartoon, this is taken from the PP7 chapter from Anna Butello and collaborators, and showing the typical density and temperature structure that we expect in a protoplanetary disk, and highlighting some of the key physical processes that we think are at work in this. So some of one of these actually mechanisms is vertical settling in radial drift due to the dust and gas having different orbital velocities about the central star. And so we would expect that, the small and the large dust would actually have different spatial distributions, occupy different spatial distribution in protoplanetary disk. And this is something that is very nicely illustrated with this data from Marion Villeneuve and collaborators showing a disk seen edge on, where you can see actually the dust scattered lines. So rising from the disk emission, this is the Ophiuchus 1631-31 disk. And so the scattered line is shown in colors. You have 12 CO gas shown in blue, and you have the ALMA continuum emission seen in white contour. So it's immediately clear that the large dust brought by the continuum emission, they have a radial extent and a vertical extent that are much smaller than what we have for the small dust brought by the scattered light, as well as for the gas. So this is nicely illustrating radial drift and vertical settling. Snow lines are also very relevant in protoplanetary disk. This is something that, as far as CO snow line is concerned, can be brought by the N2H plus emission. It's the idea that N2H plus emission will arise wherever in the disk CO is not in the gas phase. So this helps indeed confirming theoretical models of the position of the snow line, and this can give us constraint about local temperatures in the disk, and snow lines can also have important implications for the growth of solid particles in protoplanetary disks. And also we have the possibility of pressure maximums or locations in the disk where the radial drift of large dust particles will be stored. And we think that this is something that is indeed needed to explain these different ring-like structures. In particular here, as you can see, different sequences of dark and bright rings in the emission. And the fact, these bright rings of emission are mostly understood as being locations where large grains would be actually prevented from radially drifting toward the central star. So there will be locations actually where the gas pressure have maximum to store the radial drift particles. Okay, so that being said, now I'm going to try to highlight, as I said before, so three main questions we have for the understanding of protoplanetary disks. The first of this question is simply, what is the mass of protoplanetary disks? One reason for raising this question is that it's intimately related to scenarios of planet formation and orbital evolution, with the idea that should we expect that class 2 protoplanetary disks should be kind of massive, because we expect that at some point those disks are like on the verge of forming planets, so that we need a decent mass reservoir to trigger the formation of giant planets, as we are, fairly expected to have, given the statistics of giant exoplanets that we have on the other hand. But maybe you could also raise the first question of, actually, shouldn't we expect these class 2 disks not to have too much mass? Because, it's possible that planet formation has already been initiated, so that part of the mass content has already been turned into the giant planets that are perhaps at the origin of the various structures that we see in the disk emission. So I think this is one reason why it's fair to ask this question. And the main issue here is that, as this audience is supposed to be very well aware of, most of the mass is in H2, which we can't see, or which we hardly can see. So we need to resort to observing all the mass contents, which are much smaller in content, of course, so dust mass or other gas species. And as far as the dust emission is concerned, the usual way, or the classical way of estimating the total disk mass from the dust emission is to assume that the dust emission is optically thin and that the scattering is negligible. And this is something that we think should be relevant at radio wavelengths. And in that case, as you can see with the formula on the right-hand side, dust mass estimation comes to measuring the average flux of dust emission at millimeter wavelengths. And provided you know this distance, you know something about the absorption capacity and the dust temperature, so we get the dust temperature. And of course, I mean, these working assumptions could be discussed. I think it's also always helpful to remember that there is a very strong uncertainty in the determination of the mass absorption capacity, which is something I like illustrating with this plot, which is showing mass absorption capacity as a function of wavelengths, and how far it depends on the dust size distribution in this, which of course we don't have so much clue of what it should be. I mean, here the minimum size is presumably like a few nanometers, and the maximum size of the dust size distribution is varied according to the color. And you have different assumptions about whether the dust is compact or porous, and different assumptions in terms of the pole or exponent of the size distribution. What is cool in a sense is that when you look at radio wavelengths, I mean, most of these curves tend to somewhat converge. However, you can have a feeling that depending on what you assume for your dust, and I'm not even talking about the dust composition, like what I see, silicates and so on, you can have like a factor of 5-ish uncertainty in the absorption capacity, which of course will be communicated to the uncertainty in the duration of the dust mass. There's also, of course, some uncertainty in the dust temperature, which needs to be known somehow. And at the end of the day, even perhaps worse, we need to assume something about the dust to H2 mass ratio, which is maybe 1%, maybe something different. So, of course, all these uncertainties propagating together give us a feeling that estimating the total mass of the disk based on the dust emission is something which is kind of tricky. We can also do a similar game playing on the gas emission, but here there are lots of caveats as well. Based on CO isotopes, here the problem is to what extent freeze out into dust grains will actually prevent from observing a potentially large reservoir of cold gas in the outer part of protoplanetary disk, which we would just be blind because of the freeze out. Regarding HD, this is perhaps most promising because there's no freeze out, but at the same time, that molecule would also emit beyond 20K. So there's a bit of similar issue, I would say. And also we would need to have the temperature vertical structure needed to prevent some degeneracy in the abundance and temperature determination. And so looking at what we have, like for a given disk, this is for TWI on the right-hand side, you can see that different techniques could end up with kind of different estimate for the total disk mass based on whether you work on the dust emission or the gas emission. So at the end of the day, you have factor of decent uncertainty factor in the determination of the mass, with, of course, interesting implication for finite plane formation and orbital evolution. A second issue we have with understanding protoplanetary disk, as far as I feel concerned, is what really drives the evolution of the gas in protoplanetary disks. One reason for bringing that in is because I feel that there has been a shift of what we think should be the dominant process at work here. I mean, up until like a few 5 or 10 years ago, we thought that the main process behind the evolution of the gas would be the turbulent radial transport of mass and angular momentum in disk, and we thought that this would be primarily driven by the so-called magnetorotational instability, which is a linear instability in disks that are dynamically coupled to weak magnetic field. And when that's the case, then the disk gas would develop a state of turbulence, a little bit like what is shown in the animation, which is showing turbulent velocity fluctuations in an MHD simulation under the conditions described in this blue sentence before, dynamic coupling and weak magnetic field. And there are perhaps two interesting things that we can take from these models and simulation. One is that the turbulent state that an MRI turbulent disk would adopt would be pretty well described actually as a viscous disk model. So we would tend to describe disks in the scope of the classical accretion disk theory. Of course, an interesting implication is that such disks would tend to have a steady state transport of angular momentum with a mass accretion rate that is in kind of close agreement actually with the stellar mass accretion rates. But there is something that is important to remember is that this MHD turbulence is intimately related to the gas feeling the action of the magnetic field. And this is something that we do expect for charged particles. And the issue is that actually protoplanetary disks are poorly ionized medium. So that is definitely where chemistry plays a crucial role, because we do need to know the ionization rate in order to have a feeling for whether the turbulent motion due to the magnetorotational instability is indeed communicated to the dense neutral gas in protoplanetary disks. So one is to worry about the different sources of ionizations in disks, which can be due to energetic photons from the central star, due to cosmic rays, also thermal collisions happening in the inner warm regions of protoplanetary disks. But as you can perhaps feel with this picture, at the end of the day, when you actually compute the ionization rate expected in disks, I mean, most of the bulk content of protoplanetary disks should be actually inactive to the MRI. So that's the meaning of the gray areas in this sketch, where the MRI is expected to be quenched due to so-called non-ideal MHD effects having to do with the so-called ambipolar diffusion and the ohmic diffusion. So at the same time, this is maybe consistent with the fact that the observations of the non-thermal broadening of line emissions seem to indicate that the level of turbulence in protoplanetary disks might be indeed very well smaller, much smaller than what is expected from these models of fully turbulent MHD disks due to the onset of the MRI. So I guess this is one good reason, and the progress of numerical simulations is another good reason, that has brought forward another view of thinking about the evolution of the disk, of protoplanetary disk, which is this time not radial transport of angular momentum, but vertical transport, vertical extraction of angular momentum by the help of so-called magnetocentrifugal wheels. In this case, I mean, this can drive some laminar accretion starting from the surface layers of the disk. And it seems that this alternative scenario for how this gas evolves has some observational support, in particular from gas line kinematics. And this shift in paradigm, I feel that this has some potential, very important potential implication for scenarios of planetary formation and evolution, which still need to be tested. And maybe this has also revived the idea that if the MRI is healed or quenched, does it leave more space for weaker, usually neglected, other hydrodynamical instabilities? This is an open question. This brings me to my next key question here, which is what is behind these numerous substructures that we see in the disk emission? So substructures seem to be found in a great deal amount of protoplanetary disks, although one should be aware that there is presumably some strong observational biases to have in mind. But indeed, it seems that, you know, looking at the dust or the gas emission, one very often finds substructures in the form of dark and bright rings of emission, as you can see, for instance, for AS209 in the dust continuum emission. But you can also have some asymmetric emission, like compression-like asymmetries, and also spirals. And you can see a few examples from a few selected ALMA disks there. It's also quite interesting that you can find all these different asymmetries when looking at a given disk at different with different observational traces, and this is the case in the upper panels with HD 14, 25, 27. And I'm just highlighting the fact that even when looking at two different gas traces, one can find kind of very different structures, which is presumably telling us something about the chemical processes, maybe having to do with the dust temperature in these disks. I guess I want to say that many of these structures are very much reminiscent to the structures that we expect from the interaction between a protoplanetary disk and its planet. And this is something that I'm showing here with the result of an aerodynamical simulation, where you have a giant planet, a Jupiter-mass planet that forms in its disk and triggers different kinds of perturbation. You can see the spiral density waves triggered by the planet. The fact that these spirals are actually shock waves implies that the planet tends to repel, to push the material away from its orbital region, so thereby carving some sort of an analog gap structure on its orbit. Can also trigger the formation of kind of non-axis symmetric vortex-like structures due to some hydrodynamical instability setting in at the outer edge of planetary gas. And all these different structures are reminiscent to the rings, to the spirals, to the Prussian-like asymmetries that I've shown you in the observation just before. So just taking one example, for instance, when we think about this sequence of dark and bright rings of emission in the dust continuum emission, the usual game, if like myself, you're in the game of thinking that there are planets everywhere, then the usual classical interpretation for the dark rings of emission is to say that there ought to be a planet sitting at the location of every dark ring of emission, as each of these planets would actually repel the gas and the dust away from its orbit. So the idea would be, is there really a planet at the location of every dark ring of emission in the disk? Which is usually what is assumed, and people will try to deduce like the mass of the planets needed to reproduce the dust continuum emission. But most of the time, and this is related to one of the previous points I made about the estimate of the disk mass, most of the disk masses would imply that as soon as you form the typical planet masses required to explain these structures, the planets will actually expected to migrate in the disk on quite short time scale because of the gravitational interaction with the disk gas, so that the structures that are predicted might not be long-lived structures, and this is a concern. So this is one reason why, with my former PhD student, Clément, we investigated the implications of planetary migration on the dynamics and the emission of the dust in protoplanetary disks. And in particular, for Saturn to Jupiter mass planets, one would expect substantial large-scale migration through the disk, which may not be actually a smooth, continuous migration. We show that the migration could be kind of discontinuous fashion, with the implication that the planet could trigger a single planet migrating this way in a disk could actually trigger the formation of multiple dark and bright rings of emission. And by migrating so close to its central star, maybe it would just not be observable by different ways, which is actually a good transition to my next point, which is to say that if we believe that planets are behind the structures that we see, then why do not we see more planets directly in the disk emission? Because, I mean, with the exception of the planets in the cavity of the PTS 70b, that's the 70 disk, maybe some one other disk, we don't see the planets directly. There are some indirect indication of planets being found in the disk, and one is the so-called velocity kinks, which is illustrated here with the observed data with ALMA of this particular disk. When you look at the gas emission in the given channel map, what you expect to have is that the channel map emission would be very smooth, very continuous. And what we see in this particular disk here is that the channel map emission has this kind of kink, this kind of discontinuity, which is thought as arising from the perturbation of the gas flow about the planet. And this is something, as you can see, with a comparison with the lower planets that is kind of well explained by this planet simulation and relative transfer calculations. I think it's fair to say that there are many other mechanisms that could actually create substructures in this and which may not have to do with planets. I'm just trying to highlight here some of the works being done in the PCMI community. So rings could arise from the formation of zonal flows in these models with magnetic winds. I'm just showing very briefly what is being said. I don't have time to explain why these mechanisms do trigger these structures. So spirals could be due to planets, of course, but they could also be due to interactions with stellar companions and stellar flybys, like in the work of Nicolas Pueyo, is something that is very relevant to the formation of protoplanetary disk in dense stellar clusters. And also spirals could also arise from remnant accretion from the molecular cloud that has triggered the formation of the disk. Okay, so in the -5 minutes left, don't have much time, but I'm taking 2 minutes just to highlight a recent work that we have conducted at ERA in Toulouse, and which is the question of the formation of the warm eccentric Jupiters. By warm eccentric Jupiters, I mean the planets that are within the red ellipse in this diagram, which is showing the planet to star mass ratio for exoplanets, for which we have an estimate of the planet mass as a function of the orbital period. It's interested in color. And so these exoplanets, these warm Jupiters, are eccentric because, I mean, many of them actually have a substantial eccentricity. The median eccentricity is about 0.3, and this raises lots of questions about how these planets acquire their eccentricity, knowing that usually due to these planet interactions, planets will retain a very low level of eccentricity. So, I mean, usually one would think that there ought to be dynamical interactions with planets or with stellar companions that have triggered this eccentricity. But with my collaborators in Toulouse, we went another way and we tried to revive a model where orbital eccentricity could actually be bumped up in protoplanetary disk when planets actually end up migrating in a cavity in a protoplanetary disk. And one reason for reviving this mechanism is because they are drawing observational evidence for the presence of cavity in the dust and in the gas emission of protoplanetary disk. And what happens is that when a planet forms outside a cavity, migrates inside, it plunges inside the cavity, and then the magic of these planet interactions can imply, don't have time to explain that, I'm sorry, can actually increase the planet's eccentricity to kind of substantial values here. You can see that in our aerodynamical models, we can end up actually with this eccentricity up to 2.3. So thinking that this could perhaps be a generic way of forming warm eccentric Jupiters in protoplanetary disk, we actually investigated what the implication or what the signatures would be of that mechanism in the dust and in the gas emission of the disk. So for that, we did 2D gas and dust aerodynamical simulations that were post-processed with gas or dust relative transfer calculations. And I'm just showing you in this single slide the result that we have. On the top left panel, you see the result of the aerodynamical simulation when the planet has reached the cavity, and when it starts to get an eccentric motion, what happens is that its spiral density waves become short waves and create some large-scale asymmetries due to the eccentric motion of the planet. This is 2 Jupiter mass planets in the disk. There's a 30 AU cavity in the disk. And when looking at the gas 120322 integrated intensity, you can see that inside the cavity here, we can see some large-scale asymmetries, which are directly reminiscent of the large-scale asymmetry triggers in the gas. You should be aware that there are some assumptions behind the derivation or behind the calculation of these synthetic maps, which would all require to have a decent chemical model to calculate the abundance of the CU. Interestingly enough, when looking at the dust emission, both in scattered light, in near-infrared, and in the millimeter dust thermal emission, we don't quite see much about the implication of the eccentric motion of the planet meaning that whether the planet is eccentric or circular in the cavity doesn't have a signature at all in the dust emission, but it does have so in the gas emission. So with that, and before being kicked out by Benoit, I would thank you and take any questions.